This course, titled BIM and Environmental Impact Integration, introduces the fundamental relationship between digital building processes and environmental performance assessment. As contemporary construction shifts toward data-driven and sustainable workflows, BIM becomes a central tool that integrates geometric, material, operational, and life cycle information into a unified digital model. The aim of this module is to provide students with an understanding of how BIM enables structured environmental analysis, supports carbon-aware decision-making, and improves the ecological quality of built environments. The lecture forms the conceptual foundation of environmental BIM workflows that are widely used in architecture, engineering, and planning disciplines. The structure of this course follows a logical progression that begins with the fundamentals of BIM and gradually moves toward advanced environmental integration concepts. We begin by defining BIM and its data-centric philosophy, followed by BIM maturity levels, information requirements, and the concept of level of detail. The module continues with environmental impact categories and standardized lifecycle frameworks, both of which are essential for connecting BIM models with lifecycle assessment, LCA. Subsequent sections explain embodied and operational carbon analyses, simulation tools, data interoperability frameworks, and the decision support models necessary for sustainable design choices. The course concludes with real-world case studies and a summary integrating all discussed topics. The learning objectives of this module focus on building students' capacity to navigate both technological and environmental dimensions of BIM. By the end of the course, students will understand how BIM operates as a digital ecosystem capable of storing material, geometric, and performance data. They will also learn to connect BIM models with environmental frameworks such as ISO 14040, EN 15978, and various carbon accounting methodologies. Critical thinking is encouraged through the evaluation of different integration methods and case studies. Ultimately, students gain the ability to use BIM not only as a visualization tool but also as a scientific platform for evidence-based ecological design. Building information modeling is a methodology for representing physical and functional characteristics of buildings in a digital environment. Unlike traditional design approaches that treat geometry and documentation separately, BIM integrates these components into parametric objects enriched with metadata such as material composition, structural properties, thermal behavior, and cost. BIM models function throughout the entire building lifecycle: design, construction, operation, maintenance, and demolition. This lifecycle continuity is crucial for environmental studies because it provides the detailed and structured data needed for LCA calculations, energy simulations, and carbon assessments. BIM maturity levels describe the evolution from simple digital drafting to fully integrated, collaborative, information-rich workflows. Level 0 consists entirely of 2D CAD drawings with no structured data. Level 1 introduces a common data environment, CDE, enabling limited information sharing. Level 2 represents collaborative BIM, where models from different disciplines are exchanged using standardized formats, allowing interdisciplinary coordination. Level 3, often associated with Open BIM, enables real-time data flow across platforms facilitated by protocols such as IFC. Environmental integration becomes progressively easier at higher maturity levels because structured, interoperable data is essential for reliable environmental analysis. The concepts of level of detail, LOD, and level of information need determine the resolution and richness of data in BIM models. Higher LODs contain more precise geometries and material specifications, which are crucial for emissions and energy modeling. For example, LOD 300 provides accurate quantities, enabling embodied carbon calculations based on material mass, density, and EPD data. LOD 400 and above support fabrication level accuracy. The level of information need complements geometric detail with semantic information, thermal conductivity, environmental product declarations, or service life data, ensuring that environmental evaluations are based on accurate inputs rather than assumptions. Environmental impact assessment in the built environment relies on quantifying effects across several categories, including global warming potential, ozone depletion, acidification, eutrophication, photochemical ozone creation, and resource depletion. These categories allow environmental scientists and designers to understand not only a building's carbon footprint but also its broader ecological consequences. When integrated with BIM, these categories become measurable through the metadata embedded in building components. By mapping quantities extracted from BIM to LCA databases, designers can evaluate how alternative materials, construction methods, or energy strategies influence environmental outcomes. Life cycle assessment is the scientific backbone of environmental evaluation. Standards such as ISO 14040 and EN 15978 define methodological stages and system boundaries. In building assessments, these are typically divided into product stage, A1 A3, construction, A4 A5, use phase, B1 B7, end of life, C1 C4, and potential reuse or recycling, D. BIM models provide quantity takeoffs and material assignments needed for the early calculation of A1 A3 impacts, which represent embodied carbon. As the model progresses, operational energy data and maintenance schedules allow designers to evaluate the use phase impacts. This structured approach ensures that all life cycle stages are analyzed systematically. One of the main advantages of BIM in environmental analysis is its ability to provide precisely structured data for LCA. Every BIM component carries metadata such as material type, volume, density, and location, all of which are essential inputs for LCA tools. Instead of manually collecting building quantities, BIM exports these values automatically, minimizing human error. When BIM is connected to LCA software, either through direct plugins or file exports, materials are matched with corresponding EPDs or database entries. This structured data flow is the foundation of accurate and scalable environmental assessment. Three primary integration approaches exist for combining BIM and LCA workflows. The first is direct integration, where LCA tools function as plugins inside BIM software, e.g., Tally in Revit, enabling real-time analysis during modeling. The second is middleware integration, where BIM data is exported, typically via IFC or Excel, and imported into standalone LCA tools such as One-Click LCA. The third approach uses API-based or custom scripts to automate the link between the BIM model and environmental databases. Each method has benefits. Direct integration supports early design decisions, while middleware tools offer more robust databases and calculation options. Embodied carbon calculations quantify emissions associated with the production, transport, and installation of construction materials. BIM plays a critical role by supplying precise material quantities. By assigning density, production methods, and transportation distances, BIM models enable accurate A1 A3 calculations. Designers can experiment with alternative materials, recycled steel, low-carbon concrete, bio-based insulation, and instantly evaluate their carbon benefits. This capability is essential for reducing emissions at the design stage, when the potential impact on the carbon budget is greatest. Operational energy calculations focus on the building's performance during use, typically covering heating, cooling, lighting, and ventilation. BIM supports these calculations by supplying geometry, surface characteristics, shading structures, and HVAC system layouts. Simulation engines such as Energy Plus and Do2 connect to BIM models through export workflows or plugins. By evaluating multiple design variations, window wall ratios, insulation thickness, HVAC efficiencies, designers can quantify energy consumption and compare environmental outcomes. Integrating operational energy modeling with BIM improves prediction accuracy and supports the design of low-energy and net-zero buildings. A variety of environmental simulation tools integrate seamlessly with BIM to support both energy and carbon assessments. Autodesk Insight offers rapid conceptual analyses, enabling designers to explore the environmental consequences of early design decisions. IESVE supports detailed thermal simulations and compliance assessments. Other platforms such as Cove Tool provide automated optimization workflows based on carbon and cost metrics. The shared objective of these tools is to provide fast and reliable feedback to guide ecological decision-making before the building design becomes finalized. Environmental Product Declarations, EPDs, are standardized documents that report the environmental impacts of products based on life cycle methodology. BIM models become significantly more powerful when connected to EPD datasets because they allow designers to evaluate the environmental performance of specific building materials rather than relying on generic assumptions. Databases such as Ecological, ICE, and EC3 contain thousands of EPDs accessible by material name, manufacturer, or region. Linking BIM objects to these EPDs ensures that carbon calculations reflect real products and supply chains. The Industry Foundation Classes, IFC, schema is a neutral, open standard format used for data exchange across BIM software. IFC ensures interoperability by defining how geometric and property data should be structured. For environmental workflows, IFC property sets can store LC irrelevant attributes such as material composition, service life, or thermal properties. As environmental modeling requires consistent data quality across platforms, IFC becomes essential in multidisciplinary projects. The use of IFC increases transparency and preserves data integrity throughout the assessment process. Decision support systems in sustainable design integrate environmental, economic, and functional performance metrics to help designers choose optimal alternatives. Methods such as multi-criteria decision analysis, MCDA, or life cycle cost analysis can be combined with LCA data extracted from BIM models. Early design stages benefit most from these frameworks because design choices, orientation, massing, material palette, have the largest impact on carbon emissions. By connecting BIM-derived data with decision support algorithms, planning teams can evaluate trade-offs and develop environmentally optimized building strategies. In the first case study, a mid-scale office building was evaluated using a Revit model connected to the Tally plugin. The design team compared 3 alternative structural systems: concrete, hybrid concrete steel, and engineered timber. Through BIM-based LCA, they discovered that the timber option reduced embodied carbon by 28%, primarily due to lower emissions in A1-A3 stages. The plugin enabled rapid iteration, allowing the team to test facade changes, insulation materials, and interior finishes. This case demonstrates how real-time BIM LCA integration accelerates design exploration and promotes low-carbon alternatives. The second case study explores a net-zero energy building designed using Autodesk Insight for energy optimization. The BIM model was used to analyze solar potential, shading, and the performance of passive strategies. High-efficiency HVAC systems and a rooftop photovoltaic array were tested to minimize operational energy. Simulation results guided envelope improvements and renewable energy sizing, achieving over 60% operational energy reduction. This example illustrates how BIM-based energy analysis supports not only environmental assessment but also long-term energy planning required for net zero building certification. The module has demonstrated that BIM serves as a powerful platform for integrating environmental assessment into the building design process. LCA, embodied carbon accounting, operational energy modeling, and advanced simulation workflows benefit from the structured and information-rich nature of BIM. Interoperability standards such as IFC and lifecycle frameworks such as N15978 ensure consistency and scientific rigor. When combined with decision support methodologies, BIM facilitates ecological design thinking and empowers planners, architects, and engineers to make informed, low-carbon choices. This integration is essential for achieving sustainable, resilient, and future-proof cities.